Hello guys, this is Avinash and you're watching Everything Metallurgy. So friends, in this video we'll look at some of the memory based questions from this year's GATE Metallurgy paper. So we got about some 20 odd questions which we look at its solutions in this video. Okay, so let's get started friends. So the first question. The first question is what they asked about is the type of indenter that's used in Rockwell C-square. Okay, so as you know guys, Rockwell's test is used for hardness measuring, okay, which is one of the type of indentation tests. And in this we have A, B, C, three scales are there, in which in A we'll be using the Braille indenter, B we use steel ball, and in C also we'll be using the Braille indenter. So what's this Braille indenter? So this Braille indenter is nothing but a diamond cone, okay, with slightly rounded tip at its bottom. Okay, so the answer is diamond cone. So you will get to see the options, like different options are there, like steel ball, diamond pyramid and all. The right answer is diamond cone. Next question that we came across in many previous year papers is the sequence. They ask the sequence of the precipitates, or the sequence of steps in precipitation hardening, okay, or age hardening. So I think in 2015 or 16 also you'll get to see this question. So this answer is firstly the GP zones will be formed, which are nothing but formation of cluster of different atoms which grow to form theta double dash, where we get to see the peak hardness, and finally we'll be getting theta. This is the equilibrium precipitate. So this is an important question from previous year itself, not nothing new from this question, but what you must remember is this graph, okay, where you can see GP zones here, theta double dash, and as I said, peak hardness at theta dash, and finally equilibrium precipitate, that's theta, okay, theta at the last. So what's this graph about? So here you can see this graph is nothing but the hardness versus aging time. Okay, so as I said, this region is the peak hardness where you can see theta dash, and the left side, that means in this region before theta dash, if you age for that time, it is called an underaged sample or an underaged specimen, and if you age it for longer times greater than theta dash, it forms theta, which is equilibrium, and it is called as overage. Okay, so this is what you must know about how the hardness varies and how the hardness varies along the sequence of the precipitates that are forming. Okay, so now we look at the next question. The next question that they asked is what is the following that does not come under the gating system of a sand casting. Okay, so firstly we have to know what is this gating system of the sand casting, and then we'll come to the options. We got different options, like one is sprue, runner, riser, and pouring basin. So these are the different options that we got with this question, and we must pick out which is not coming under this gating system. Okay, so which is not the part of the gating system, and the answer is pouring basin. Why? Because if you see the mold, if you take the cope and the drag parts, Okay, what you get to see, first of all I'll draw something and then I'll explain. Okay, so if I think this is my sand casting, the upper part is called the cope, this is the drag. Okay, so here if you see this vertical part, wherever, okay, you can see this vertical part over here, this is called a sprue, which allows to flow of the metal. Okay, and then comes different areas or different paths through which this the metal go, and these are called gates, or before gates it goes into the runner. So in this particular thing we only have one runner, so the metal will flow only in one horizontal path, that is a runner. If in complicated structures, then you can see metal may flow into different paths. For example, as I said, this is a runner, these are called gates. Okay, and now what is the other option that we have? Razor. So razor is usually here somewhere, protruded kind of thing, and this is very important because it helps to cut down the defects that are forming in the casting. Defects in the sense, if you find any shrinkages in the metal, then this razor will be giving the extra metal to solidify, or you can say the last liquid that is solidifying is present in this riser. Okay, so that it, wherever any shrinkages form, the metal that is present in the riser goes down and removes that defect. Okay. So the answer, as I said, is pouring basin. So pouring basin, what is pouring basin? Pouring basin is something which acts as a funnel, you can say, above the screw. Okay, where we pour the metal. So this is the pouring basin. So the answer is pouring basin, which is not coming under the gating system. Now, the next question. The next question they asked is the number of atoms that are present, the number of atoms that are present per unit area. Okay, the number of atoms per unit area for a plane 100, and what they gave is the crystal, where the crystal is of Pb, that is lead, and it is FCC. So this is the given information. They gave us the plane, they gave us the crystal structure FCC. Now what they are asking us to find out the number of atoms that are present per unit area. Now this is a tricky question actually. So usually what they asked is the number of atoms divided by the area of the plane. Okay, so this is what they asked. So now what is the question is, they gave an FCC. Okay, firstly you must know what is an FCC crystal looks like. I think everyone must be knowing it now, where you have all the 8 corner atoms, and there are different face centered atoms here. Okay, so now they asked to find out the 100 plane. So if you consider this as an origin and this is my 100 plane, what I have is something like this. Okay, so this is my 100 plane, and in this, this is the phase diagonal. And if you see for phase diagonal or in FCC, what you can see is that you can see here R plus 2R plus R. So R plus 2R plus R will be equal to root 2A. So if I consider A is the side of this cube, so this will be A, this will be A, and it's a right angle. So what we get is a root 2A. So here 4R is equal to root 2A and A is equal to 2 root 2R. This you must know because this we are using it here in this area. And if you see what is the number of atoms here, so if you have at the corners, you have 4 atoms and each is contributing 90 degrees or 1/4 of a sphere, right? So 4 into 1 by 4 plus 1 complete atom is present in this. divided by what is the area of this. So this plane, I am considering it as a cube. Obviously it's an FCC, so its area will be a square. So here if I take it, 4 will be cancelled, so 1 plus 1 will be 2 atoms divided by a square. So again 2 by, I can replace a with 2 into r. So what I am getting is 1 by 8 r square. So this will be 1 by 4 r square is my answer. And from here you can directly do, because we don't remember the r value, but the r value is given, you put it here and you will be getting the answer for this question. Okay, now the next question that we are looking at is, I think this is the 5th question now. Yeah, so the 5th question that we are dealing with in this video is nothing but it's again a simple formula based question where they gave some lattice parameter A which is equal to 0.124 nanometer, and they gave the crystal structure, that is BCC, and they are asking to find the larger interstitial atom that can accumulate or that can go into octahedral void. So this we know directly, right? So for BCC, the largest atom that can go into the octahedral void is 1.555 R. Whereas for FCC it is 0.414 R. So by putting this formula 1.555 into 0.124 nanometer, so the answer will be 0.155 into 0.124. So I'm calculating here, and we will be getting 0.0192. Okay, 0.019. So this I think they have asked to round off. So they asked to round off to 2 decimal, so it will be 0.02. Next question is, this is an interesting question. Actually, they directly asked from a theory question actually. What is the condition for a superplastic material? So they directly asked to find out what is the condition for this superplastic material. So usually what are all the conditions? So we'll discuss that. So firstly, the temperature should be greater than 0.5 times the Tm. That's the melting point. Must have a low strain rate so that no brittle fracture is taking place, and also fine grain size is required, and the strain value, it should be obviously greater than 100 percentage, or rather 100% to 1000 percentage. We see from the definition of superplastic material only this condition should be coming. And the last and important one is high strain rate sensitivity. So this is the option that you can see in the paper, and this is the correct answer. So they gave some tricky answers like high strain rate sensitivity, low strain rate sensitivity, low strain hardening coefficient, etc. But there's nothing to do with the strain hardening thing in superplastic materials. So the answer here is strain rate sensitivity. Okay, so this is the given condition for superplastic material. Okay, now one more question, simple question that they gave is a matrix which has a det of -9 and another matrix n has a det of -14. So what they asked is a det of n into m. Okay, so they asked the det of nm. So we have a direct formula where it is det m into det n, that is -19 into -14 into -9. So here the answer will be 14 into 9, that is equal to 126 is the answer. Okay, so this is a simple maths question that we encountered in this year's paper. Now one more direct question that we saw is they asked the number of elastic constants for an isotropic material. So here what is an isotropic material, you must know. Okay, so if you know this, you'll directly get the answer right. So isotropic material is something in which you can observe same property or same value of the property in any direction. That is, it is invariant with the direction. So if you take an elasticity, it will be same in all the x, y, z, or whatever direction you take, you will be having the same constant value. Okay, the opposite to this is anisotropic material, where there is a change of material properties with respect to the directions. So here they asked for isotropic material. So usually if you consider, what we have is only one elastic modulus. So you can take the elastic constant to be equal to 1. But let's see what they take, because usually for an isotropic material they consider elastic modulus as well as Poisson's ratio to be the elastic constant. So it may be 1 or 2. And one more question is they asked cupola furnace. Cupola furnace is used for dash. So the answer is cast iron. Okay, so it's the direct question. Cast irons usually are melt using this cupola furnace, and the options are also similar. Like they gave plain carbon steel. So obviously, plain carbon steel is used or is produced using an LD converter or an electric arc furnace. So okay, they confused by giving like plain carbon steel, cast iron, etc. And the answer is cast iron. Now, one more interesting question, and I like this question, is they gave a function where y equal to square bracket x, and what they mentioned is this symbol is defined such that, defined as, it is the greater integer function. Okay, it is the greater integer function. Now what is this greater integer? And one more thing they mentioned is x belongs to the range 1 comma 4. Okay, and they asked to find out the area under this graph in this region. Okay, so what is this greater integer function? So it is nothing but it denotes some number which is some integer which is less than that. For example, if I get x equal to some 2.2, then greater integer function of 2.2 will be 2. Similarly, from 2.4 it will be 2, 2.8 it will be 2. For 3.1, the greater integer function is 3. That means this greater integer function is something which denotes an integer, or you can say the greatest integer which is less than that number. Okay, so now they asked to plot a graph for this. Obviously we have to find out the area. Okay, so here we have 1, 2, 3, 4. Similarly here, so as I said, it's a greater integer. From the value of x of 1 to 2, we will be getting a value of 1. Okay, it's the same for the values of 1 to 2. For the value of 2, okay, what is this? It's simply equal to the integer itself, because it is greater than or equal to that number. So the next will be 2 until 3, and until 3 to 4, it will be something like this. Okay, so this greater integer function is something like a steps kind of thing. So now they ask to find out the area under this. Okay, so it's very easy. If you divide it into 3 triangles, what you get? This is 1, 1, this height is 2, this is 1 again, 3 minus 2, and this height is 3, and this is 1. So the area is 1 into 1 plus 1 into 2 plus 1 into 3, which is nothing but 6. 6 is your answer. Okay. These are some of the basic questions, 1 mark questions that we encountered in this paper. Now we look at some of the 2 mark questions. So we'll look at some 11th question. So this question is usually based on the Bragg's equation. Okay. So what is the Bragg's law? Bragg's law, you know, 2d sine theta is equal to n lambda. So this is a pretty straightforward question. Okay. So what they gave is theta equal to 24.65 degrees and wavelength lambda also they gave 0.1543 and the material is an FCC material. Okay, and what they asked is they asked to calculate the lattice parameter for the first peak. So as they gave it's a first peak, so we have n value 1. So on putting all this, what we get 2d sine 24.65 degrees will be equal to 1 into 0.1543. I'm letting it in nanometer only because I'm also calculating d in terms of nanometer. Okay, so on calculating this, one more thing, what is d here? D is the interplanar spacing, and we have a formula for d equal to a by root of h square plus k square plus l square. Okay, now what is the first peak that we are encountered in our FCC, or what is the plane that we get the first peak? It is nothing but the closest packing plane, that is 111, or you can also tally using the conditions for FCC as it is given FCC, which should be either all or odd or even. Okay, so it must satisfy the conditions for this. Now, so by replacing that, what we get, 2a divided by root of 1 square plus 1 square plus 1 square is 3 into sine 24.65 degrees equal to 0.1543. So I'm calculating here 0.1543 divided by 2 into 3 divided by sine of 24.65. Oh, I think I messed up. I just open the gate calculator and calculate. Meanwhile, you also calculate and comment down the answer that you got here. 0.1543 into root 3 divided by 2 divided by 24.65 sine of. Okay, so we got the lattice parameter of 0.320. So this is the answer. I think for this also they confused us by even 0.37, 0.35, etc. But the answer is 0.32, and this 2 is important because if you forget this, you will be getting 0.64 as an answer, and there is an option for these 2. So don't make such silly mistakes. So this answer is 0.32. Okay. One more question that which I liked a lot is from the desulphurization index or the desulphurization ratio, because I did the same video in my channel before. Okay, so what is this desulphurization ratio? Usually it's denoted by L and is given by 50 here. So it is nothing but the percentage of sulfur that is present in the slag divided by the percentage of sulfur that is present in the metal or the melt after the desulphurization, because usually in these problems they'll assume that there will be no sulfur content initially in the slag. So here also they gave the same condition. Okay, so this formula implies L equal to the percentage sulfur that is present in the slag after desulfurization by the percentage of sulfur, or the final percentage of sulfur that is present in a melt after desulfurization. So we'll write the conditions that they give us. So initially what we have percentage sulfur in the metal is 0.03 percentage, and what is the weight? It is 1000 kg. Okay, so in 1000 kg of melt we have 0.03 percentage, and also what they gave us is the final sulfur. Final percentage sulfur is 0.015 percentage. Okay, so here if you see initially for 1000 kg and 0.03 percentage, how much is the sulfur weight? How much is the weight of sulfur that I have? Is nothing but 1000 into 0.03 divided by 100. So I'm getting how much? 0.3 kg. Okay. Similarly, finally also how much sulfur I'm left with? Finally, as I said, it is how much? 0.015 by 100. So here I am left with 0.15 kg. So if you see here, initially I have this much amount of sulfur in my steel. Finally, it got reduced to this much. So where is the remaining going? That means where is this final minus initial going? It is going into the slag. So how much it is? 0.3 minus 0.15. We have 0.15 kg of sulfur in our slag. Okay, this is the weight. So now bringing back our formula, we need L equal to 50 and this equal to, we need the percentage, not the weight. So we want 0.15 divided by X. This is the percentage where I am assuming X to be the weight of the slag. This is what we have to calculate. So we have to calculate the weight of slag used for this treatment. Okay, so I am assuming this to be X and I am using in this formula. Now, after the reaction, what is the sulfur content left in the steel? That is 0.15 divided by, what is the weight of the steel is 1000 into 100. So this if you cancel out, this is also cancelled. What I am left with is 50 is equal to 1000 by X, and this is equal to 520 is 100 and X equal to 20 kg is my slag used. Okay, so this is a simple formula based question which is for 2 marks in this year, and also we have covered pretty same example in my previous videos which is presented in my iCard. Okay, so the answer is 20 kg of slag. The next question, I think it's 13th question that we are dealing with now. So the next question is, this is also pretty much interesting actually because they clubbed 2-3 concepts in this. So what they gave is that they asked to calculate the time of filling of the mold. Okay, so firstly, what is this T filling means? So this is nothing but usually the volume of the mold divided by the area of cross section into the velocity with which the metal is flowing. Okay, now what they gave here, they gave the volume as 10 meter cube, they gave the area of cross section of the screw is 0.2 meter square, and they also gave the gravitational force 9.8 meter per second square, and they asked to calculate. One more thing which they gave is the height of the screw is 0.5 meter. Okay, so what is this screw? Just in this previous video also I have drawn about this. So this is my cavity, the vertical path is my screw, and this height what they give, this height is 0.5 meter. Now we have to calculate the velocity. So in our basic physics we know that the kinetic energy will be equal to mgh, the potential energy, if it is some h height above my reference frame. So here if I consider my lower part of the sprue as the reference frame, it is above h, that is 0.5 meter. So this gets cancelled, and the velocity with which we get is root 2 gh, which is root 2 into 9.8 into 0.5, which is again 1 by 2. So this gets cancelled. So what we are left with is root of 9.8. Okay, which is again my 3.130 meter per second. Okay, so this is how they clubbed basic physics concept of velocity, energies into our time of filling concept. So now easily we can find this, right? Time of filling will be equal to volume 10 divided by area 0.2 into velocity is 3.130. Okay, so by calculating this, how much will be getting? We'll be getting 15.97 seconds, and I think I remember they asked to round it off to the nearest integer, which will be 16 seconds will be my time of filling. So this is how we have to calculate, and remember this formula is what should strike you, and then this concept. Okay, so this is one of the nice question according to me. I like this question in this year. Now one more important concept from thermodynamics. I felt thermodynamics questions are very less in this year's paper, but one of the question is very good, so that we'll be dealing with. So what is this? So here what they gave is, they gave a reaction C plus O2 refresh 2 CO, I guess. I don't remember the reaction. I think CO or CO2 they gave, and what they gave is the delta G for this reaction is minus 19840 minus 40.65 T. Okay, so this is what they gave, and again units I am not bothered in this question because all the units are same. So and what they gave is at 1800. So this is steel, usually you can say decarburization of steel. So at 1800 Kelvin temperature, what I am getting, I am having 0.03 weight percentage of oxygen in my steel. So what I must calculate? I must calculate the percentage carbon. So usually from thermodynamics, what we know from this equation, if we want to know the equilibrium constant, we'll be taking PCO by the weight percentage of carbon. So this is equal to C into O2 equal to 1 by K, because it's a gas, so it's in standard state, it will be of 1. So this usually is called the carbon oxygen product. Okay, so the inversely proportional. If you get to know that the oxygen content in the steel is very much less, it indicates that my carbon is high, or vice versa. Okay, now we'll come to this value. So they said at 1800 degrees. So we'll be getting 19840 minus 40.65 into 1800. Okay, so now what we get is my delta G value, that is 19840 minus 40.65 into 1800, and this comes out to be minus 93010 joule per mole. Okay, so this is my this thing, and from thermodynamics we know delta G equal to minus RT ln K. This is equal to minus 93010. So minus minus will be cancelled, and here you can put these values of R ln of K is again C into O2 equal to 93010 divided by R. They gave the value 8.314 into 1800. So on solving this, what we get? We will be getting ln K. Okay, this comes out to be somewhere 6.2150, and by putting these values, we will be getting this E into O2 will be equal to e power of. So if I am considering ln into E, so on the right hand side I will be getting e power of 6.2150, and this will be equal to 500.2388. So we know oxygen, it is given as 0.03 percentage. So by putting an inversing, what we get is, so here if we do C into 0.03 equal to 1 by 500, that will be equal to 0.00199. Okay, so if you take back the carbon, you'll be getting 0.066. So I think they asked to round it off this also, so you'll be getting 0.07 percentage of carbon will be your answer. This is an integer type question. This is a good question, easy question if you know the formula of carbon product. The equilibrium ratio, and this it's just mathematical solving. Okay, now the next question. Next question is again they gave thermal diffusivities. Okay, so 100 into 10 power minus 4 centimeter per second. If we do for 1 hour, there is extent of diffusion, and if the diffusion rate is this, how much will be the time? So you know dT is equal to constant, or D is inversely proportional to time. If the diffusion rate is more, the required time for diffusion is less. So using this simple concept, what we get? 100 into 10 power minus 4 into 1 hour equal to 25 into 10 power minus 4 into x hours. If I do it for x, then what I get, I will be solving for x equal to 4 hours. Okay, so I'll be getting x equal to 4 hours. The next question, they directly gave a formula which looks like this: dA by dN will be equal to delta K cube. So what's this? This is nothing but the crack growth rate, and delta K is my stress intensity factor root. Okay, so what is this? This is nothing but the form of Paris law. Now what they gave is they asked to calculate what happens if the crack length is doubled. What happens to crack growth rate? This is what they asked in the question. Okay, it's pretty straightforward, right? So by putting these values, what will get? Delta, this is a constant, pi is a constant, so we are left with root a whole cube. So dA by dN will be equal to a power 3 by 2. Now I'm taking this as a crack growth rate as C. Okay, so now what we want C1 by C2 when the crack growth is doubled. So we want C2, this is 2 power 3 by 2 into C1. Okay, so we want this That's nothing but root 8, and we are getting 2.82 C. Okay, so that means if the crack growth, or sorry, if the crack length is doubled, then the crack growth rate will increase by a factor of 2.828. Okay, so this is the question that we saw in our paper this year. Okay, and also they asked some simple questions, like they asked the principle of dipenetrant. So this is an important topic from NDT. This question is from NDT. Why? Because in every year you will get to see this kind of question. One, what is the principle of this? So this is nothing but capillary action. Okay. Similarly, there are for other also, like for ultrasonic, what is the principle? For acoustic, what is the principle? So you must know all the principles of these NDT techniques. Okay. So these are the questions that we got to see. And now one more important thing that you must consider are matchings. So I think around 4 or 5 they gave, and we got some 4 matchings here. So I'll quickly write down the options. This is one matching where they gave the elements in one side, and they give different properties: ferromagnetism, superconductor, semiconductor, and one more thing they gave is a diamagnetism. So matchings are always straightforward, right? So especially in this years, you can see only straightforward matchings. So here, if you know, iron is a ferromagnetic material, mercury is a superconductor, silicon is a semiconductor, and copper is diamagnetic material. So directly, if you take this as PQRS, you will get P4, Q2, R is 1, and S is 3. Pretty straightforward matchings. So other two matchings also are present. So here they gave about a property, okay, like semiconductor, superconducting, etc. And here what you can see is the technique of production or extraction. So you have match melting, carbothermic reduction. I think this is given as flash smelting. Okay, so any type of smelting, you can see the option. Metallothermic reduction, and one more is electrolysis. I think Hall Herold or fused salt electrolysis they gave. Yeah, I think it's fused salt electrolysis. And the options are iron, titanium, copper, and aluminium. So again, this is pretty straightforward. So matte smelting is used for copper, carbothermic carbon reduction is done in iron, metallothermic for titanium, and electrolysis for aluminium. So here if you see P3, Q1, R2, and S4. Okay, and we have one more matching where again they ask the process names directly, like Midrax, Corex, basic oxygen furnace, and submerged arc furnace. Okay, and you will get to see on the other side they gave pig iron, sponge iron or DRA, anything is the same. Ferrochrome, which is a ferroalloy, and the other is simple oxidation. I think this option, I think, or they can also take steel according to this. So midrex is used to produce sponge iron or DRI. 4x is used to produce pig iron. BF has oxygen or steel. And submerged dark furnace is producing ferrochrome. So P2, Q1, R4 and S3. And the other matching which is based on application. So if you see, this is by property, this is by the method, and this is by also method, and one more thing is again the application. Ductile iron, grey cast iron, zirconium alloys, and one more thing they gave is beryllium copper alloys. And the options here are nuclear reactor, valves and pipes. As I already said, this is based on application. Basis of structure, heavy structures and bearings. So again, these are direct applications. Ductile iron is used for valves, for sewage applications. Zirconium alloys are used for nuclear reactors. Grey cast iron for heavy structures, and bearings are beryllium copper alloys. So here P2, Q3, R1 and S4. Okay, so this is based on application. So here if you see matchings only, you got about 4 matchings, so around 8 marks. Okay, so these are some of the memory based questions that you encountered in this year, and let me know in the comments whether if you want to a detailed solution of GATE 2020 once the official question paper is released. Do let me know so that I'll be trying to do it. And if you made till this part of the video, please hit the like button and also share to your friends and subscribe to Everything Metallurgy. Thanks a lot, guys. Thank you so much.